Alright, so this is simultaneously a response to one of the posts in the discussion boards, as well as an experiment with dock cams, because as I mentioned in the last video I posted, my son busted my iPad. So I'm going to see if this dock cam works okay. So we've been talking about generating functions and the usefulness and utility of generating functions. And a point was brought up about how while each sequence does give rise to a generating function, it's unclear whether or not the generating function could actually be useful or meaningful. And that's entirely right. It's certainly possible that you have just some out of this world strange sequence that gives rise to a generating function whose functional form doesn't lend any insight at all into how the sequence behaves. So, but I did want to point out that while this is true, generating functions still allow us to get our hands around a far greater class of sequences and their closed forms than the techniques we've already had up to this point. So let's go ahead and write out a fairly straightforward recurrence relation. Let's say we have a sequence whose recurrence relation, let's say a naught is 5 and a sub n plus 1 is just 3 times an plus 2, right? And so what this would mean is that you would start with 5 as the 0th term, and the next term you would take that, multiply by 3, and add 2, so 15 plus 2 is 17. The next term you would take that, multiply by 3, and plus 2, so 51 plus 3 would be, plus 2 would be 53, and so on. So the issue with this sequence and trying to find a closed form is this pesky plus 2 business, right? Like if it were just 3 times an, we'd get a very nice, quick geometric sequence out of that, and we'd just go, oh, it's 5, 15, 45, so on. And even if it was multiple order, if a sub n plus 2 was something an plus 1 plus something an plus something before, as long as we didn't have a constant part, we could utilize the methods of finding the characteristic equation, finding its roots, and then getting the appropriate exponential sum of exponentials to be our recurrence relation. But with a sequence like this, because the plus 2 gets added on in every term, there isn't necessarily a nice, clean way to directly just solve a characteristic equation and get that sequence. Now, there's a number of ways to get this sequence, but I just want to point out that generating functions is a perfectly good way to figure out how to get our hands at closed forms of the sequence. So let's go ahead and get started on what we would do here. We know in general from an plus 1 is equal to 3an plus 2 that an plus 1 minus 3an, that's equal to 2, right? And if that's the case, then an plus 1 minus 3an times x to the n plus 1 is always equal to 2x to the n plus 1. Right? So far so good? So we just subtract over and we multiply both sides by x to the n plus 1. Now the reason I chose x to the n plus 1 is this x to the n plus 1 matches up with that an plus 1. So that'll make sense in this next step. What I want to do next then is take infinite summations of things that look the same on both sides. So if I take n from 0 to infinity of an plus 1 minus 3an x to n plus 1, that's the same as a sum from 0 to infinity of 2x to the n plus 1, right? All the terms are the same. We said so ourselves, right? The coefficients are always the same. That means these monomials are the same. And that means the sum of those monomials, even if they go up to infinity, have to be the same. And so this is where things get a little strange with the algebra, but just bear with me. The first thing we want to do is take advantage of the distributivity of sums and group things separately, right? So we have a sum from n equals 0 to infinity a sub n plus 1 x to n plus 1 minus 3 times the sum from n equals 0 to infinity a sub n x to the n plus 1, and that's still equal to our sum n equals 0 to infinity 2x to the n plus 1, right? All we've done here is redistribute the sum. And so now you know, if I look over here, the smallest power I get is, if n is 0, I get x to the 1, a1. And then when n is 1, a2, x2, a3, x3. So this term here, this really is just the sum from n equals 1 to infinity a sub n x to the n. Now over here, I have a n, but x to the n plus 1. I want my x powers and the index of my coefficients to match. But I could do this by factoring out an x. What's left is a sum from 0 to infinity a sub n x to the n. And what we want from that is for, well, that's still equal to the sum from 0 to infinity 2x to the n plus 1. And so, sorry, and you know what, I'm just going to do one more rewrite here. I'm going to change that. Again, the same issue, right? My coefficients here are always 2, but my powers when n is 0 starts at 1, and it goes 2, 3, 4, 5. So I may as well re-index this. So I just start at 1. 2x to the n. Alright, now for all of our nice closed form power series representations of functions, we usually sum from starting from 0 to infinity. This is also consistent with how we get Taylor series representations of functions, right? And so I would like to be able to rewrite both of these things in such a way. I'd like to be able to add in a sub 0 to the left-hand side and the appropriate amount to this side. And so if you remember, a sub 0 is 5. So why don't I just add 5 to both sides? Why don't I take 5 on the left and 5 on the right? If I do that, then this 5 is equal to 5 times x to the 0, right? X to the 0 is just 1. So that's just a0, x0. And so I can use that fact to rewrite this to be the sum from n from 0 to infinity a sub n x to the n. Oh, my pen here is not doing so great. I guess it is blue going forward. Minus 3x, the exact same series representation. And that's going to be equal to, all right, let's take a look at this. If I want this to be something I recognize, I probably want to start at 0 and have 2x to the 0, which again is just 2. But 2x to the 0, I can find 2 out of this. I just got to split 2 off of this 5. So I can rewrite this as the sum from n equals 0 to infinity, 2x to the n, right? What I've done is gone from n equals 1 to n equals 0 by adding in the extra 2. And I do so by taking 2 away from that 5, right? So there's only 3 left there. So, putting all of this together, what this gives me is I have 1 minus 3x times the sum n equals 0 to infinity a sub n x to the n, that is going to be equal to, well, 3 plus, and I look at this thing, I can factor 2 out, and from the reading or from previous classes, we may remember that just the sum from n from 0 to infinity of x to the n is 1 over 1 minus x. So I can simplify that to 2 over 1 minus x. And that means that this sum from n equals 0 to infinity a sub n x to the n is equal to 3 over 1 minus 3x plus 2 over 1 minus x, 1 minus 3x. Right? And let me see if I can get this done in some more. The punchline here is that 3 over 1 minus 3x, that's 3 times 1 over 1 minus 3x, which is the sum n equals 0 to infinity of 3 to the n x to the n plus 2 times the sum x to the n to 0 to infinity, sum n goes from 0 to infinity, 3 to the n, x to the n. Alright. So what's the punchline of being able to do all of that? Let's say I want to find the 1000th term of the sequence, right? That's the coefficient corresponding to x to 1000 on the left hand side, right? Now, if I did this with the recurrence relation, I would have to start from the very beginning, right? 5, 1753, and count up to term number 1000, which seems like a lot. Now, this isn't exactly doing a ton better, to be honest, but it is still an improvement. I can take 3 times 3 to 1000, that's no big deal, and I can compute the corresponding 1000th coefficient of this, right, by knowing that that's x to 0 times 3 to the 1000th x to 1000th. So this isn't 0, so a sub 1000 is equal to that 2 times 3 to the 1000th plus 3 to the 999 plus 3 to the 998, etc., etc., etc. So this isn't a great sum to compute, but I can still compute it with a lot fewer calculations, a lot more directly than it would take to have generated the first 1000 terms of this sequence directly. So my main point here is just to show that generating functions, while they're not a panacea to all of the possible issues that could come up with solving sequences or recurrence relations, give us another tool that lets us get our hands around them that we couldn't get with the methods we've already learned. All right, I hope that was helpful. I hope that this was reasonably legible, and that just know that probably, unfortunately, not in time for this class, but eventually I'll get something working again. All right, thank you.